Today, we are covering a polar form of complex numbers. Now, complex numbers are not new for you. We used complex numbers in college algebra. You've used them most likely in algebra 2, maybe even in geometry. So you've used complex numbers a lot. So the first part of our notes are going to be a review of some reminders, pulling on our previous knowledge, if you will, on complex numbers themselves. And then we're going to go into how we can translate them into polar form, just like we did our notes, how we ended last week together, Thursday, when we talked about converting to polar form. So when we talk about an imaginary number, it is when we have I is equal to the square root of -1. We also can take, and if I were to square both sides, I squared is also -1. And so we will commonly use both of these versions when we're simplifying. When I look at the square root of -9, I can think of this, I know this is one too many steps and you wouldn't necessarily need all of these steps. I can think of this as the square root of -1 times the square root of 9, where the square root of -1 gives us I, and then the square root of 9 gives us 3, so we have 3I. Okay. The complex number is in Z. So Z is equal to, when you see Z, you can think, okay, complex number. We've also had other numbers as R. So R is the real number system, things like that. So Z is the complex number system when we talk about numbers and where they're located. A and B are the real numbers, but when I add in the I to the B portion, that is when it becomes a complex number itself. All right, the complex plane, the horizontal axis is the real axis. So when we think about that, what we would have called the x-axis is now the real axis. And then our y-axis is now the vertical one, and this is our imaginary axis. And we can still graph things in both planes if desired. On slide 2, we'll actually do that. We're going to plot the number 3 minus 4i on the complex plane. So 3 is the real number part, and 4i is the imaginary. And if you want to or need to put it into a coordinate system, you certainly can. It's not typical to write it as a coordinate number, but we go to the right 3 units for the real part. And then since it's -4i, we go down 4 units for the imaginary part. So this point here is in fact 3 minus 4i when we graph it. And we're going to be graphing a lot of them when we convert to polar form. We also can add our complex numbers by combining like terms just as we normally would. So we would consider this as 3 minus 4i plus 2 plus 5i. Adding the real number parts, 3 plus 2, we know is 5. And then -4i plus 5i gives us just 1i. Similarly, we can subtract. So I'm subtracting 2 plus 5i from 3 minus 4i. So I'm going to start with 3 minus 4i. From here, I'm going to subtract 2 plus 5i. Right, so we might want to convert this by distributing that negative so we don't forget about it, and then combining. So 3 minus 2 is 1. -4 minus 5 is -9i. We also can distribute and multiply using our imaginary numbers. So I can multiply 4 times 2 plus 5i by multiplying everything by 4. So 8 plus 20i. And we can even use the distributive property. So bear with me here. We've got 2 times 1, 2, 2 times 4i plus 8i, negative 3i times 1, negative 3i, and negative 3i times 4i I know is negative 12i squared. Well, I can combine the middle two, combine like terms. So we're at 2 plus 5i. However, I also have I squared here, and I squared I know is negative 1, right, from that first page. So if I replace I squared with negative 1, I'll really have positive 12. So I can combine one more time, giving me 14 plus 5i. So anytime we've got that I squared, we'll want to convert it to help us simplify. All right, and the last question to review is if we have to divide complex numbers. When we divide complex numbers, very similar to our radicals, we don't want to have radicals in our denominator. So we rationalize the denominator. We'll do the same thing here, except we're going to multiply by the complex conjugate. So when I look at 4 minus I, its conjugate is 4 plus I. And so I want to multiply the numerator and denominator by 4 plus I. And then, of course, now we've got the binomials times the binomial, so we're going to go ahead and multiply. All right, we'll have, and double check my work here. I'm going to go a little quickly because this should be a review. Let's see here, 8 plus 2i plus 20i plus 5i squared over, all right, so I'll multiply the denominators, 16 plus 4i minus 4i minus I squared. All right, it will happen by multiplying by the conjugate. We've got a difference of perfect squares, if you will. And so the middle will always cancel or create a pair of zeros, which is very useful. In the numerator, I can combine my like terms here. And I've got 5 times I squared, which is negative 1. So I really have 8 minus 5, which is 3, plus 22i left when I combine like terms. In my denominator, though, I'll have subtract I squared. So subtract negative 1. And subtracting negative 1 is obviously the same as adding 1, thus 17. So notice we were able to get rid of the complex number in our denominator, and that was the goal by multiplying by the conjugate. Oops. There. All right. So now that we've got a little bit of a review of the basics. So part of your assignment is going to be doing review of imaginary or complex numbers. And the other part will come what we're going to talk about today. From our last lesson, and something that we've been continuously working on since we started our right triangle trig, we know that cosine is x over r, sine is y over r, and then of course tangent is y over x, where r squared can be found by taking the sum of x squared and y squared. Okay. But now the only thing we've done differently is when we're talking about complex numbers, we know that the x value is our real number system and the y value is our imaginary system. So I now am placing an I with my y portion. So that's where I'm getting z is equal to x plus yi. Or more formally, we are going to utilize r times cosine of theta plus I times r sine of theta. So this is what we're going to use to rewrite a complex number using polar coordinates. So let's think about our first example here. It says, express the complex number 4i using polar coordinates. Well, let's first draw a picture. I'm a visual person. Right now, I know that 4i is the same as we have no real number part plus 4i. So if we think about how we would graph that, again, we have the real number system going left and right. So I'm not going left or right. I'm just going up 4 units up here. So this is now the point 4i, where the distance between here, of course, would be 4 units, right? Because I went up 4 units. Now, when I think about theta value, because if I want to put it into polar coordinates, I'm going to need theta and my radius. Well, I know my radius is 4, right? Because that's the distance to the point itself. Happy day. And I know using standard form, when I move my theta value, if I start here and go up 90 degrees counterclockwise, I know I'm at pi over 2. So I have found my radius, which we said is 4, and theta is pi over 2. We have found the two things with which we need in order to write polar coordinates. Thus, 4i is equal to, so now we look at the formula here, the radius times cosine of theta, pi over 2, plus I times the radius of sine of pi over 2. And of course, I know it looks weird to have I4. You can certainly put 4i sine. Like if it makes you feel better to put the I after 4, please feel free. I'm just putting it this way because that's what the formula says. So you're not like, well, where do those values come from? Okay. So let's formally define this on our next slide. So the polar form of a complex number we just said is this. Remember, z is complex number. So a complex number can be written as r times cosine of theta plus ir sine of theta. But we can also utilize another formula. Z, a complex number, is equal to the radius times Euler's number, right? E is just like pi, like an irrational number, to the power of I theta. It's called Euler's formula. So we will use both of these formulas together. And our good friend Euler, he was from the 18th century. He did lots of cool things in math, but he was from the 18th century, but this is his formula. Okay. And again, all we need in both instances is we need a radius and we need theta. Find the polar form of the complex number -8. Well, I don't have an imaginary number here. I just have the number -8. So really, I have -8 plus 0i, if you need to have that portion there. Again, our real number system is going horizontal, and the imaginary is vertical. So if I wanted to graph -8 plus 0i, I would start at obviously 0, 0 and go left 8 units. And I'm not going up or down on the complex number system or the imaginary number system. So the distance from here to here is 8 units. So I now know my radius. In standard position, as I come towards my point, I know that I'm going a distance of pi for theta. So now I have the two pieces that I need to write using Euler's formula. Our radius of 8 times Euler's number E to the power of I theta, and theta is pi. To double check, I'm going to set this equal to the right-hand side. Our radius is 8 times cosine of theta, which is pi, plus I times our radius of 8 times sine of pi. And maybe I'll just go like this and say, I'm just going to double check to make sure we believe that these are the same. Don't always have to double check, but just to kind of show our work. We know that cosine of theta using our unit circle is -1. I know that sine of pi on our unit circle is 0. So this part is null and void because anything times 0 is 0. Thus, I have 8 times -1, which is in fact -8 where we started. And I think that writing it using Euler's formula with the Euler's number is much easier to write than all of the stuff on the right-hand side. Although they're equivalent, it wouldn't matter to me. It is just more convenient. All right, so the past two examples, we have posted points on the imaginary axis and then the real axes. But what if, such as example 9 and 10, our points are not on the axis? What if they're somewhere in one of the quadrants? How can we find theta? How can we find the radius? And then put it into polar form. Okay, so I'm going to first start off by graphing what does -4 plus 4i look like? What quadrant are we in? So I'm going to start going by left 4 units, 1, 2, 3, 4. And since I have positive 4i for my imaginary portion, I will go up 4 units. So it looks like I'm over here in the second quadrant. We can still bring our triangle and drop that right triangle that we're used to doing. And I need to know what is theta coming from standard position to where we are. We don't know. And we also want to know what is the radius. We don't know what the radius is, but we do know the distance, right? So I know that radius squared is equal to each of these parts squared, right? I went left 4 units, so I've got -4 squared. Plus, I also went up 4 units. Maybe it'd be helpful if I labeled these just in case. So radius squared is 16 plus 16. And radius squared, of course, is 32. We can take the square root of both sides. When I take the square root, I do want to try to simplify my radical if possible. I know that 32 is 16 times 2. I can take the square root of 16, which is 4. So 4 square roots 2. All right, so now we've got the radius. We don't yet have theta. That is our next mission, is to find theta. We can use sine, cosine, or tangent. We're going to use one of each in the upcoming examples so you can see what it looks like for each one. I'm going to start with using cosine. I know that cosine of theta is our x value over the radius. And in this case, our x value is the real number of -4, and we just found the radius 4 over square roots 2. Well, this does simplify to -1 over square roots 2, but we want to rationalize our denominator. And this will give us then negative square roots 2 over 2, which is on our unit circle. It is on our unit circle. So cosine is negative square roots 2 over 2 at 3 pi over 4, which makes sense because 3 pi over 4 is in the second, or the second quadrant. So now that I know theta and I know our radius, we can utilize Euler's formula to put it into polar form. So our radius is 4 square roots of 2 times Euler's number to the power of 3 pi r theta over 4i. I know it looks weird. I know it looks kind of like uncomfortable, maybe something that you've not seen before, but trust me when I say you're golden. All right. Similarly, we've got -3 minus 5i. This time it looks like we're going to be in the third quadrant, right? Because I go 3 to the left on the real numbers axis and then 5 down on the imaginary axis. You can drop that right triangle that we're used to. I want to find all the way around from standard position. I need to know what is this theta. I also need to know what is my radius. I know that since I went 3 to the left and I went down 5, we can use r squared is -3 squared plus -5 squared to solve for our radius. See here, 9 plus 25, r squared is 34. So our radius has to be square roots 34. It's not divisible by a perfect square. It's 17 times 2, and neither of those are a perfect square number. All right, we just need to find theta. Let's use tangent this time. We haven't used tangent in a while, so let's use tangent this time. I know tangent of theta is opposite over adjacent. So in our case, opposite would be the imaginary and adjacent would be our real number. So -5 over -3, which of course reduces to 5/3. When I look on my unit circle, I don't have any of sine over cosine as 5/3. That's not going to be very useful for us. So we have to use the inverse of tangent. So we'll still have to utilize that from time to time if it's not on the unit circle, which gives us a decimal. In this case, that decimal is 1.0304. But friends, we know that, we use this one. We know that 1 is in the first quadrant here. So when I'm thinking about radians, 1.0304 is here. I need to know all the way around. So I would need to add pi to this in order to find my angle in the third quadrant. Therefore, theta has to be, I'm going to say about because it is rounded, 4.1720, which makes sense because when I think about here is pi is 3.14, and we're just a little bit more. So we're just a little bit more than pi. Well, now I have the two things we need to write polar form using Euler's formula. The radius, square roots 34, times e to the power of 4.1720, our theta, I. So yes, it is possible that our theta is a decimal in our exponent. So don't be alarmed when you get weird numbers like that. All right, this time it looks, we've got square roots 3 plus I. This time it looks like we're in the first quadrant, where I'm going to the right square root 3, and we went up 1 unit, 1 I, if you will. So r squared is 3 plus 1. So r would have to be 2, right? Because 3 plus 1 is 4, and the square root of 4 is 2. That's a nice neat radius is 2. Right, so we've used cosine, we've used tangent. Let's use sine this time. Sine of theta. I know sine is opposite over hypotenuse, so opposite is 1. Hypotenuse we just found is 2. Where is sine equal to half on our unit circle? Of course, we know this. It's pi over 6. If you didn't have that memorized, you still have use of your unit circle until the end of the semester, of course. And now we have our radius, and we have pi over 6 for our theta. Thus, our radius times e to the power of pi over 6, our theta I. And we spent time looking and creating those polar forms. We're going to use what we've created, kind of build off that in the upcoming examples. So in the next case, notice I have 3e times the power of pi over 6i, and I want to put it into complex forms. I want to go backwards. Well, I am given all of the things that I need, right? I am given my theta, and this time I'm given my radius is 3 rather than 2. Using Euler's formula, we can expand this as the radius times cosine of pi over 6 plus the radius I times sine of pi over 6. And if you are able to evaluate, we should, to reduce this down to a complex form of a plus bi, I know that cosine of pi over 6 using my unit circle is square root 3 over 2. And it's going to be 3 times that. So 3 square root 3 over 2. And I know that sine of pi over 6, well, hey, we just saw that was half. We just used that in our previous example. So we'll have plus 3 halves I, right? Because 3 times half is 3 halves. And we just wrote it in complex form. I apologize for my error here. It should says to compute, not to computer. Compute a power of a complex number. So we were probably looking at -4 plus 4i to the power of 6. I mean, I got this. I know how to multiply binomials. I can do that, right? I know you know how to do that. So, but there's lots of room for error. If you were to start saying, well, I'm going to take 4 plus 4i, and I know I need to multiply this by itself 6 times, you might be here a little while. Not that you couldn't do it. It's just not efficient, right? And so you would start, of course, by multiplying these two together and simplify. You would get another complex number, which then case you would multiply that complex number with the next -4 plus 4i. And there's, whether we want to believe it or not, there's really room for a lot of error. Even a small misuse of a positive or a negative would certainly ruin all of the hard work you would have done. And there's lots of places that you could make unintentional errors here. So we can utilize Euler's number to help us simplify this in a more efficient manner. So notice it says we're going to first start by converting it to polar form. Then we're going to raise polar form to the power it's given and simplify using our exponent rules, and then put it back into a plus bi. So then put it back into complex form. So while it seems like a lot of steps, it's not. And you'll be a lot more efficient with your time. And then further, a lot less room for error. We converted -4 plus 4i. Remember, this one was one of the first ones we did. We were over here in the second quadrant. We converted that into polar form in example 9. So I'm going to say number 1, we did example 9. We converted this to polar form, and we said it was 4 square roots 2 e to 3 pi over 4i. So we've done step 1 already back in example 9. Step 2, let's raise this to the power that we have. So it's raising this to the power of 6, because 6 was our power here. I will have 4 square roots 2e 3 pi over 4i to the power of 6. I know that everything on the inside needs to be raised to that power. So I'm going to do 4 square roots 2 to the power of 6, and then I'm also going to do e 3 pi over 4i to the power of 6. Here's calculator work. Easily plug that into your calculator, and we're going to get a pretty large number. Don't be alarmed. 32,768. Now let's look at the e portion. I have a power to a power. Recall that when we have a power to a power, we multiply those powers together. So I'm really going to have, let's say I could actually simplify this, because 6 over 4 would be 3 over 2. So it only reduces to 9 pi over 2. So I'll still have e to the power of 9 pi over 2i. Step 3, put it back into a plus bi. I have my radius and I have my theta. So I know this is equal to 32,768 768 times cosine of theta, 9 pi over 2, plus I times 32,768 times sine of 9 pi over 2. Well, think about 9 pi over 2, right? What is it coterminal with? So if I start with 9 pi over 2, and my goal is to get it to where I can maybe use the unit circle to help me determine what those values are. I know that 9 pi over 2, if I were to subtract 2 pi, I could subtract 4 pi over 2, so that's 2 pi, and I would be at 5 pi over 2. Is that on our unit circle? Maybe not. Subtract another 4 pi over 2. Well, now I'm at pi over 2. So these are all coterminal with pi over 2. And pi over 2 is on our unit circle, right? It's right at the 90-degree mark. So I can evaluate. I know that cosine of pi over 2 is 0. So this just disappears. 0 times anything disappears. I know that sine of pi over 2 is 1. So all I have is 1 times I times 32,768. So 32,768 I is the final result. Does it seem like a lot of steps? Perhaps. If you were to multiply like we would up here, you would simplify to that bottom number. It would just take you a little while to get there. So this would be the easier route when you just take some time to think about what we're doing. It certainly is useful. Right. Let's talk about de Moivre's theorem here. We just stated that the complex polar form is equal to r times cosine of theta plus r times I sine of theta. And you would agree that since both of them have r, we could factor r out. So z could also be r times cosine of theta plus I sine of theta when we factor out the common factor. Moivre's theorem says that if we raise that complex number to a power, it is the same thing as saying raising our radius to that power times cosine of our theta times the power plus I times theta of the power again. So notice that the power is showing up in the 3 locations, once within each portion. So when I think about finding, it's asking us to use de Moivre's theorem to evaluate 9i, and it's the square root. So this is different than the ones we had been working with. The ones we had been working with would have just said 9i. Here I have the square root of 9i. So this also would be the same if I convert this from a radical to an exponent. This is the same thing as saying 9i to the power of 1/2. Right, because it's the square root and all of this is to the first power. Where would this be graphed? If I just think about 9i, it is 0 plus 9i, so I am on the imaginary axes up here. Where I know my radius is 9, because up here is 9i, because I went 9 units up. And I know since I'm on the imaginary axes, this is 90 degrees or pi over 2. Okay, so now that we have it here, we can now write this as polar form, excuse me. I lost my brain for a hot second. So this is the same thing as saying our radius, 9 times e to the power of our theta, I, and all still to the power of 1/2. So we've got this written to our power of 1/2. So our power, our n, is going to be 1/2. Let's expand this then. This will then be our radius to the power of n, or 1/2, so 9 to the power of 1/2 times cosine of 1/2 times our theta, pi over 2, plus I sine of 1/2 times pi over 2. I know 9 to the power of 1/2 is 3, because if I put this back in, it'd be the square root of 9, where 1 goes on the inside and the denominator is my index of my radical. Square root of 9 is 3. I'll then have cosine 1/2 times pi over 2 gives us pi over 4. I times sine of pi over 4. Well, what is cosine of pi over 4? Using our unit circle, cosine of pi over 4 is square roots 2 over 2. And sine of pi over 4 is also square roots 2 over 2. So thinking about the multiplication of 3 so we can get rid of our parentheses, I'll have 3 square roots 2 over 2 plus another 3 square roots 2 over 2 I, because we can't forget about this guy here. So I just converted or evaluated the square root of 9I. We will be able to do slide 9, but we'll leave slide 10 for class on Thursday because we won't get to that. But this will be a good place to start. And I apologize, please change this to 3 square root 3 plus I. Notice the difference in this particular one. I've got the square root of 3. I is not with the square root of 3, it's separate. Okay, so when I think about the graph of this, we did this one in example 11. He was over here in the first quadrant where our radius was 2. And let's see here, this was 1 and square roots 3. So we did this back in example 11. So let's put this into polar form. And we found from example 11, its polar form was 2e to pi over 6I. The only difference now is I'm putting 6 as my exponent. Therefore, 6 is my n. And I can utilize de Moivre's theorem to help us rewrite this and evaluate. So I'll start with my radius squared. This is my radius to the n, 2 to the 6th, excuse me, times cosine of 6n times my theta of pi over 6 plus I times sine of 6 times theta of pi over 6. 2 to the 6th power calculator work for us, so 64. Cosine of pi, since 6 times pi over 6 is pi, plus I sine of pi. And then, of course, evaluate when we can. I know cosine of pi is -1 because we are over here. And sine of pi is 0. So this doesn't matter because it's 0 times anything goes away. All I have is 64 times -1, which is just -64. Friends, that is much easier here as well. Instead of taking square root 3 plus I times itself 6 times, right? We don't have that kind of time, right? We'd be here all day. Lots of room for error.